Alright, we are dealing with Taylor polynomials and approximations day number 2. So yesterday, or the last video, we learned that the Taylor polynomial is basically this, centered at point C. It's named after this dude named Brooke Taylor, an English mathematician. We also said that if it's centered at C is equal to 0, okay, then this is the actual polynomial here. It's named after Maclaurin, who's another English mathematician. I don't know, maybe these guys were best friends or not. Colin Maclaurin, he was like, hey, Brooke Taylor did all this work. I'm just going to make C is equal to 0, and I'm just going to turn it into a new polynomial and call it the Maclaurin polynomial. I don't know. He stole his thunder, I think. So let's get to an example here. Okay, so find the third degree Maclaurin polynomial for e to the x. Remember I said you have to memorize this, so hopefully we can go back and remember it. So we get the polynomial, which is the third degree polynomial, which is equal to 1 plus x plus 1 times x squared over 2 factorial, right? Plus 1 times x cubed over 3 factorial. And that's what I get. Remember, these ones, okay, those ones, and even in front of that as well, is basically the first derivative at 0, the second derivative at 0, the third derivative at 0. So that's where that comes from. Okay, use your answer in A to find this value. So what I want to do is I want to take this limit as it approaches 0, and this is our f of x here is basically what we found right there. So I'm going to plug that in. So it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial minus 1 over 2x. Well, this positive 1 and that minus 1 are going to cancel, right? So that's going to go away. So I'm just left with really x plus x squared over 2 factorial plus x to the third over 3 factorial. All of that is over 2x. Well, now, because you get the 0, like if I plugged in 0, right, that's not good. Okay, that's not good. So how do I figure this out? Well, what we can do is hopefully we see that we have an x in everything here. Like there's x, right? So we're going to say this is the limit as x approaches 0 of x times 1 plus x over 2 factorial plus x squared over 3 factorial. And all of this is over 2x. Well, now this x and this x are going to cancel. And I'm left with the limit as x approaches 0 of 1 plus x over 2 factorial plus x squared over 3 factorial. All of that's over 2. But now if I plug in 0, this goes to 0, this goes to 0. So I get 1 plus 0 over 2. So the limit is equal to a half. All right, so that's your answer for part B. The limit as it approaches 0 is a half. Great. That wasn't so bad. Here we go. Now, suppose the function f of x is approximated near x equals 0 by a third degree Taylor polynomial. So here's our third degree Taylor polynomial. And we are going to find the value of f of 0, f prime of 0, f double prime of 0, and f triple prime of 0. So what do we know? Well, we know that these terms go in order. Okay, we know that these terms go in order. So this is really, the first term is going to be f of 0. And then it's really, so it's f of 0 plus, and then it's f prime of 0 times x, right, over 1 factorial, plus f double prime of 0 times x squared over 2 factorial, and dot, dot, dot. So this first piece is f of 0, so we already know from the very beginning that f of 0 is equal to 2. Okay, so that was pretty easy. But what about f prime of 0? Well, f prime of 0, we can see that there's no singular x term right in here, like between the 2 and the negative 5x squared. So because there's no x term, we know that f prime of 0 also has to be 0, because 0 times x is going to be 0, and this is going to disappear. All right? Well, what about f triple prime of 0? Well, f triple prime is negative 5x squared, right? This is the term that this is going to go with. And this is the actual term of the second degree there. So I'm going to take the second degree, which is f double prime of 0, times x squared over 2 factorial, and this is going to be equal to 5x squared negative. I'm going to take that term, set it equal to what the actual term should be. And now I'm going to manipulate it so that I can cancel and figure out what f double prime of 0 is. Because that's my ultimate goal. I want to find out what f double prime of 0 is. So I'm going to multiply both sides by 2 factorial. But then I'm going to actually divide both sides by x squared, right? So the x squareds are actually going to cancel. So I get f double prime of 0 is equal to negative 5 times 2 factorial, which is actually negative 10. So f double prime of 0 is going to be negative 10. Then I got to find the triple prime of 0. Well, what's the triple prime? That's the next term in the sequence. So that is f triple prime of 0 times x to the 3 over 3 factorial. That's equal to, now the third degree here is positive 8x squared. Or I'm sorry, 8x to the third. Let's multiply and divide. So I'm going to hopefully realize that it's going to be the same as 8 times 3 factorial, which is 8 times 6, so that's 48. And that's the value for the triple prime of 0. F triple prime of 0 is positive 48. Does f have a local max, local min, or neither at x is equal to 0? Justify your answer. So for right now, we don't really know much about what's happening. Okay, we don't really know much about what's happening. So it's really not enough for the first derivative test. Remember the first derivative test. Okay, it's really not enough for that because we don't have the first derivative here. Like, we know that f double prime is 0. Okay, we know that that's 0, but we don't really know everything else about the function. Okay, so does it switch from positive to negative or negative to positive? Because all we know is f of 0 and f prime of 0 and f double prime of 0. It doesn't help us to find out the value, like what happens on the left side of 0, what happens on the right side of 0. We know at first derivative, we know there's some sort of critical point where it could be a min, it could be a max, it could be an inflection point, and it might not be a min or a max, right? We don't really know. So what do we have to do? Let's use the second derivative test. Let's use the second derivative test. Okay? Well, what do we know about the second derivative test? Well, first, this is what we know. We know the first derivative at some point is equal to 0, right? At 0 is equal to 0. The second thing we can find is what happens at the double derivative. So say the double derivative at that point is positive. That means it's concave up. So this is really what the second derivative test is telling us. It's really concave up, and that means we have a relative min, right? Relative min at some point a comma f of a. All right? Well, what happens if the double derivative is actually negative? That means it's concave up, or I'm sorry, concave down, and that means we have a relative max at a comma f of a, right? So hopefully that rings a bell. If the double derivative of that point is equal to 0, this is actually inconclusive. Like, we don't know what's going on. And that's pretty similar to the first derivative, right? We know that the first derivative is 0, so it has some value there. We don't know what it is, but we can't really figure it out. And if the second derivative is 0, we can't really figure that out either because we don't know the values to the left or the right. So what do? Well, we know that the first derivative is equal to 0. So this potentially could be a min-max or a point of inflection. Okay? And then the double derivative at 0 is equal to negative 10. So because the double derivative is equal to negative 10, and the first derivative is equal to 0, we know that we have a concave down function, and therefore we have a relative max at x equals 0. Now, we cannot find the y value because we don't actually know the actual function. This is the approximate value of the function, right? This is the approximate value of the third degree polynomial. So we don't know the actual function. And so because we don't know that, we don't know the y value. But that's okay. We can still approximate the x value as saying x equals 0. We know that there's a relative max, or a local max. So remember, relative and local mean the same thing. All right, let's go on to the next page. Find the 8th degree Maclaurin polynomial for f of x equals cosine x. So remember, this is one that you probably should have memorized, or we talked about from the last video. But in case you didn't, let's go through it again. So f of x we know is cosine x, right? F prime of x is equal to negative sine x. F double prime is equal to negative cosine. F triple is equal to positive sine. And f to the 4th derivative is equal to now positive cosine. And then that's going to be cyclic, right? It's going to keep going. F of 0 is equal to 1. Remember, Maclaurin polynomials are centered at c is equal to 0. So I'm plugging 0 in, I'm finding the value. F prime of 0 is equal to 0. F double prime of 0 is equal to negative 1. F triple prime of 0 is equal to 0. F 4th derivative is equal to 1. And then you can see it's obviously cyclic from there. So we can say that, okay, the 6th degree polynomial, I'm sorry, I need 8th degree, not 6th degree. Oh, it does say, okay, so I'm going to do one thing. Let's change this to 6th degree. Okay, it doesn't, let's change it to 6. Just make it easier. That's what my notes have, but we'll just change it to 6th. Just, it's fine. It's not a big deal. Okay, so 6th degree polynomial. We know that from the last video, right, that's going to alternate, right? So it's going to be positive and negative, and then positive and negative, and so on all the way through. And because it's cosine, it's going to be even functions, like the exponents are going to be even. So this is going to start at 1, and then it's going to be minus x squared over 2 plus x to the 4, or I'm sorry, 2 factorial over 4 factorial minus x to the 6th over 6 factorial. Well, you know what, let's keep it at 8. Might as well if it's already there. Plus x to the 8 over 8 factorial. So this is what your 8th degree polynomial expansion of Maclaurin polynomial is. Okay, remember, it alternates always positive and then negative, positive, negative, positive, all the way throughout, however many degrees you're going to want to go. So this is our answer for part A. Okay, fantastic. Well, now let's use that to approximate part B. So let's approximate part B. I'm going to scroll down a little bit. I'm going to lose this, but that is okay, because hopefully you have it written down. And, well, let's just write it again, right? Let's just write it again. So the 8th degree polynomial was 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6th over 6 factorial plus x to the 8 over 8 factorial. So there we go. There's our 8th degree polynomial. Now, use your answer in A to approximate the value so that the error in your approximation is less than 1 over 500. Then we got to justify our answer. Well, if I look at this actual function here, this might be a little too difficult to do. If I split the integral, I get 0 to 1 of 1 over t squared dt minus 0 to 1 of cosine of t over t squared. Okay, now you might be able to do some integration by parts. Okay, this one's easy to do, right? This is fine, but this one might be an integration by parts, but it might take you a little while. So what we're going to do is, because it's said to approximate the value, we're going to use this Taylor function, or Maclaurin series function, as our cosine of t. Okay, so I'm going to take the integral from 0 to 1 of 1 minus, now everything in here is going to be flipped. The signs are going to change, and I'm going to plug this into cosine of t. So it's 1 minus 1 plus, I flip the signs, t squared over 2 factorial. You see I changed the values x to t because I'm in t's here. Minus x to the 4 over 4 factorial plus x to the 6th over 6 factorial minus x to the 8 over 8 factorial. And all of this is over t squared. And that's dt. Oh, these are t's. I don't know why I changed them back to x's. I knew I left them as t's, but I didn't actually leave them. Okay. So now, what do I do? Well, I can cancel, right? 1 minus 1 is going to cancel. So that's going to be pretty easy to deal with. Okay, that's going to be pretty easy to deal with. And now what? Well, if I look at the top, okay, if I look at the top, I can factor out a t squared. So let's do that. So this is the same as saying 0 to 1 of t squared, and this is going to be over t squared, right? So those are going to cancel, and I'm left with 1/2, or 1 over 2 factorial minus t squared over 4 factorial plus t to the 4 over 6 factorial minus t to the 6th over 8 factorial. And those are going to cancel, and I have that left. Okay? Now what? Well, now, because I have t squared and like I don't have any denominators that are bad, right, I can just automatically take the integral of this already. So this is the same as this. I'm just going to multiply these numbers out. Okay, I'm going to multiply these numbers out. So this is just 2, right? 4 factorial is 24. 6 factorial is 720. 8 factorial, I don't know what that one is. I got to use my handy dandy calculator. So let me do that. 8 factorial. All right, I'm going to leave this as 8 factorial. After all that work, that's like 40,320. I don't feel like writing it, so I'm just going to leave it as 8 factorial. It's kind of crazy, but okay, we're good. So let's actually integrate this, right? So this is going to be 1/2 t minus t to the 3 over, right? I got to divide it by 3, so literally that's 3 times 24, which is 72, plus t to the 5 over, and then 720 times 5. So let's do 720 times 5. 720 times 5 is 3,600. Oof, these are some big numbers. Minus, and this is going to be t to the 7 over 7 times 8 factorial, instead of figuring out that math, from 0 to 1. Okay, from 0 to 1. So from 0 to 1, all right, let's plug in the values. Okay, we are going to get 1/2, right, minus 1 over 72 plus 1 over 3,600 minus 1 over 7 times 8 factorial, whatever the heck that is. And then if I plug in a 0, that's all going to cancel. So this is really what I am getting. Now, let's figure some stuff out. What do I do with this value? Like, what is the purpose of this? Well, a couple things. We know that since the terms are alternating, so since the terms are alternating, they are alternating, right? Positive, negative, okay? And they decrease in magnitude, right? So they're going to be alternating. They're going to decrease in magnitude. Right? They're going to get smaller. Obviously, hopefully you can see that they're getting smaller. And they do have a limit of, this is probably going to go to 0, right? If I keep doing all this, right? So the limit is going to approach 0. Going to approach 0. I can't spell. But approach 0. Approach 0. If I keep adding terms, right? And those values, the further and further and the more values I'm going to get. So this one's going to be a plus something, minus something. If I were to keep on going, plus something. These values are going to approach 0 as they're going on. So like 1 over 3,600 is already really small. But 1 over 7 times 8 factorial is like 1 over 280,000. So that's going to be even really small, right? And it's going to keep going and going and going. So because those three are going to hit, we know that the error, or the absolute value of the error, has to be less than something, which has to be less than 1 over 500. Well, where does this function start becoming less than 1 over 500? So like here is 0.5, right? 0.5. 1 over 72 is 0.0 something, 0.01 something, probably close to 0.015, okay? 1 over 3,600 is definitely smaller than 1 over 500. So this 1 over 7 times 8 factorial actually didn't matter in retrospect. That's probably why it changed it to 6th term instead of 8th term, right? But I went with the 8th, and that's okay. So because this 1 over 3,600 is already now smaller than 1 over 500, we know that the error has to be smaller than that. Okay, the error has to be smaller than that. So the absolute value of the error has to be less than one of the terms in your expansion, which is then less than whatever we're trying to find, which is 1 over 500. So because the error now is 1 over 3600, like it's going to be smaller than that, we take the terms to the left of it and we combine those. So 1/2 minus 1 over 72, which is going to be about 35 over 72. So this here is our approximate value of that function from 0 to 1. Okay, we're going to estimate the function, and that's our approximate value, 35 over 72. All right, fantastic. Not too bad. Not too bad. Now, I want to use your calculator to find the actual value of this function. So how do I go about doing that? Well, I'm going to take my calculator. Hopefully it pops up here. It does. Okay, and I'm going to just plug it in, right? So you get, I get math 9, okay, from 0 to 1, 0 to 1, of the function 1 minus cosine t. So I'm going to open parentheses, 1 minus cosine of x. That doesn't matter if it's t or not. And I'm going to, let's see, close, and I'm going to divide all of that by t squared, or x squared. And then it's going to be dx, right? So dx, and I get about 0.48. So this function here, from 0 to 1, of 1 minus cosine t over t squared dt, is approximated as 0.4863853762, okay, and keeps going. Well, what's the error that you found in the approximation you found in part B? So what's that value? Well, what did I find in part B? I found the value in part B to be 35 over 72, which if you do this on a calculator, you get about 0.486. Actually, I'm going to do it right now. I'm just going to pull it up here. So 35 over 72, and I get about 0.486111 repeated, right? So let's go to the fourth decimal place. Let's keep going. Let's go to the sixth. Let's go to the sixth one. Might as well, right? So if I take this at the sixth, and I subtract 0.486111, I get about 0.000274. And that is the error. 0.000274. So that's a pretty small error. So we approximated using Taylor-Maclaurin series, right? Actually Maclaurin, because it was centered at 0. And we got an error less than 2/10,000ths of a number. Less than 2/10,000ths by approximating it to the 8th place. And really, we didn't even need to use the 8th place, right? We only needed to use 6 because that's where the error was definitely smaller than the error that it wanted to find. So it's pretty good, right? The more and more we go and more terms we use in the Taylor and Maclaurin series, then the closer and closer and closer we're going to get to the actual function being mimicked using those Taylor-Maclaurin series. So that's it for day 2, I guess. And we will, I guess, look in the next video. So deuces.